All right, good afternoon, everyone. Okay, so I'll be talking about sum product networks, and here's the outline for today. So I'm first going to introduce what are sum product networks, then we'll see how we can use them to do inference. We'll talk about some applications, and then after that we're going to get into more depth where I'll explain what are some of the relationships with, for instance, other types of probabilistic graphical models like Bayesian networks. We'll talk about specific algorithms for parameter estimation, as well as structure estimation, and then also how can we do some of the computation in an online and distributed fashion. Okay, so as I get going, feel free to interrupt me at any time, and then I welcome questions, so it'll be more interesting if you guys stop me and ask questions along the way. Okay. So what is a sum product network? So a sum product network is essentially a deep neural network that has certain properties, and in fact you can think of it as a restricted class of deep neural network where it has only sums and products. Okay. So this was proposed in 2011 by Pedro Domingos at the University of Washington, and then since then there's been lots of interest, so especially here at the University of Waterloo. So my research group as well as Ellie's research group have been advancing the state of the art, and then so there's some interesting reasons that we're going to see today. So sum product networks have some clear semantics. They have some interesting properties, at least from a probabilistic and statistical perspective, and then they actually do not suffer from several of the problems that other types of deep neural networks have. Okay, so in any case, you've got here a picture of what is a sum product network. Beyond the fact that we've got sums and products, the other thing to realize is that the network itself is going to be an acyclic directed graph, and then in the leaves we've got here some indicator variables, or more generally speaking we can have univariate distributions. So this is going to be something different than other types of deep neural networks where normally you have just features that you feed in. So here, when I talk about indicator variables, they can be indeed features just like in any other type of neural network, but more generally they can also be univariate distributions, which will allow us to think of them as some form of hierarchical probabilistic model. Okay, so in terms of introducing sum product networks, I've already talked about how we can view them as some type of neural network. But then in terms of neural networks, what's interesting about them is that they come with some clear semantics. So we're going to see this in a moment. And then the other view is that we can think of them as a probabilistic graphical model, just like Bayesian network and Markov networks. But then one nice advantage is that it's going to be a class of tractable probabilistic graphical model. Okay? All right, so let's delve into the details now. So when we look at it from the perspective of a deep neural network, some of you might say, well, we've got sums and products here, but how is that really a neural network? Because the classical view of a neural network is that you have essentially a linear combination of inputs, and then at every node after that there's a nonlinear activation function, right? So if I want to see this, where every node could be essentially a unit, as in any other type of deep neural network, then what is the nonlinear activation function, and how can I see this as a neuron, just like in other neural networks? So the answer to this is that I can actually rewrite the computation that I'm doing here in such a way where the sum node, I could transform it so that instead of just taking a linear combination of the inputs, so here when I have a plus and then a 2 and an 8, it would mean that I take 2 times this variable plus 8 times this variable. So that's a linear combination, but it doesn't look like I have any activation function. Now what I can do is actually work in the log space and then simply use a log activation function that will bring this down into the log space. And then from there, I can after that reinterpret my product node as simply a sum in the log space, right? So if you take the log of a product, right, then you get a sum in the log space. So then product nodes are really just going to be the sum of the inputs, and then after that I might want to get out of that log space, so I can use the exponential function to essentially produce a nonlinear activation function and then get back into the regular space. So with this view, we can in fact show that mathematically having a bunch of sums and products is the same as having a neural network where you alternate between layers where you take the log and then layers where you take an exponential function. Okay? Yeah?
Is the main purpose of this to avoid underflow and overflow?
Very good question. So it is not the main purpose, but that is actually a very good purpose. So indeed, when we write sum product networks, the natural thing to do is just say, well, I've got sums and products, so I'm just going to code that up to use sums and products, and then you run into underflow, overflows, and so on. But once you work into the log space, then you can avoid all of those problems, and in fact, all the stable implementations of some product networks, indeed do use this transformation and work in the log space, and then as a result are much more stable. So like for instance, we're going to see in a moment that a sum product network can be used to compute probabilities. These are normally between 0 and 1. But when you multiply lots of probabilities together, you can get a number that is very close to 0. And at some point, the computer is just going to round it down to 0. And that just screws up everything afterwards, right? But if you work in the log space, then you don't have any problems. So you're going to get the log of a number that's going to give you something negative, a very large negative number, but you can work with this and there's no problem. And then in other cases, it might not compute probabilities, but it might just compute some scalar. And then whenever you've got sums, the numbers might just grow. And then if you want to avoid some problems, again, working in a log space prevents this type of blow up. So in fact, this is common in other types of neural networks. But here, with this transformation, then we can essentially mitigate this problem a lot.
Will it be able to estimate every function? Like
Okay, yeah, that's a great question. So, okay, so here, let me see, is this the right time to answer this? I might as well answer it now. Okay, so some product networks are essentially encoding multilinear functions. Okay, so the parameters are going to be the weights. These are the numbers that I have on the edges. And then we have weights essentially only on the edges that are below the sum nodes, so that we can interpret the sums as essentially taking a weighted combination of the inputs. And now, if we think of the sum product network as essentially a function of the inputs, then we can show that it will be a multilinear function of the inputs. Okay, so it is a restricted class in this fashion. Now we can make that class more comprehensive if we have some shared weights or some shared components. Then we can essentially obtain polynomials. And then at that point, once you've got polynomials, it is actually a very rich class. And then there's already been some work showing that polynomials of a high degree with enough components can approximate arbitrary functions as well. Yeah. Okay, any other questions? Yeah.
Is the sum only between two nodes? It says x1 bar, so I'm assuming that's the probability of not.
Right. Okay, so here, yeah, I'm assuming that I've got binary variables just to keep the example simple. And so that's why this is not x1 and this is x1. So it's a binary variable. But then I could have arbitrary discrete variables. And in fact, I could have here univariate distributions that are continuous, like a Gaussian or a Poisson or anything from the exponential family. Yeah. Okay, so in terms of the advantages, we're going to see in a moment that some product networks provide clear semantics. I'll explain this in more details, but basically it will have to do with the fact that they compute probabilities and we can interpret what they're computing indeed as probabilities with respect to some features. We're going to see as well that some product networks are naturally a generative model. So there's a lot of interest in recent years to obtain generative models in deep learning. And then there's been a lot of work to take non-generative models, modify them, and obtain something that's generative. In the case of some product networks, you don't have to do anything. They are naturally generative models. We'll see in a moment how that works. And then we'll talk about training. In fact, we can use lots of techniques for training some product networks beyond just gradient descent. So most packages out there make available several optimizers that are typically based on gradient descent. We're going to see that, for instance, we can use here the expectation maximization algorithm, and I'll show you how we can formulate this as well as an optimization problem, in fact, a type of signomial program for which we can compute various relaxations that lead to various algorithms that are more effective. They'll have a superlinear convergence that is better than gradient descent. Okay, and then finally, we'll talk as well about structure estimation. So here, there's a network that has a certain structure in the sense that you see there are nodes with a graph that essentially defines the computational graph. But where does that come from? So we also have some algorithms that allow us to estimate what would be a good graphical structure for the network. Okay. All right, so let's go on now with the probabilistic graphical model view. So how many of you are already familiar with Bayesian networks or Markov networks? Okay, so all right, so it's not everyone. So in any case, if you're not familiar with those, it's not the end of the world. So I guess in the space of graphical models, the most popular types of probabilistic graphical models are Bayesian networks and Markov networks. And then these networks are typically used to represent joint distributions over a set of variables. This set can be quite large. And then what makes them interesting is that then they can encode some direct dependencies in terms of the edges between the nodes. Or they can also encode some correlations, again, based on the edges between the nodes. So probabilistic graphical models have been around for a long time, and then they've been quite successful in terms of modeling different things. But then they tend to have an important drawback, which is that in general, if you want to do inference, then it might be intractable. So what I mean by inference is simply asking what is the probability of one variable given some evidence. So this is a basic query that you might ask. And then answering this when we have lots of variables with different probabilistic dependencies might lead to some intractability. And in fact, it is known to be sharp P hard. Okay, so in computational complexity, actually, who knows what is sharp P? Ooh, okay, not too many people. Who has heard about NP hardness? Okay, very good. So NP hardness is often what is used to define, the boundary between tractability and intractability, right? So with NP hardness, it means that there are problem instances where it might take at least exponential time. At least at the moment, we don't have any better algorithms to obtain something that would always be polynomial time. Okay, now sharp P is even harder than NP. Okay, so here the intuition is that with NP, a classic problem would be the satisfiability problem, where in logic you have some formula and then you want to find a satisfiable solution. Sharp P is essentially the problem where you count how many satisfiable solutions there are. Okay, so that's a relationship, and you can see intuitively right away that it's going to be a harder problem because not only do you have to find a satisfiable solution, but you must find all of them and count them. Okay, so now how is that related to inference? And the idea is that when you do inference, you're essentially counting all the joint assignments with their weights, and then the probability or the answer to a query is essentially the sum of the probabilities of all those satisfying assignments. Okay, so that's the relationship. Okay, so for traditional probabilistic graphical models, in general, then we have this bottleneck where we can't do inference tractably, so we're going to have to approximate. But now with some product networks, what's interesting is that it is also a probabilistic graphical model, but it has a different view. So here the view is that the nodes do not necessarily correspond to random variables and the edges do not correspond to correlations or probabilistic dependencies, but instead the nodes, they correspond to operations, and then the edges, they define the computational graph, so how you're going to do the computation. Okay? So that's a departure from those networks, but then this is very much in line with what happens in deep neural networks, where the network is also just defining a computational graph. Okay, and then for inference, what's interesting is that this class of networks is guaranteed to be tractable. So we're going to see in a moment that to answer probabilistic queries with respect to a sum product network is going to be in the class of polynomial time, so we can guarantee, in fact, that we can find the exact solution in linear time with respect to the size of the network. Okay, any questions about this? All right, let's keep going. Okay, so now let's talk a bit more about how we can do inference and how we can use sum product networks to represent a joint distribution over several random variables. So here, I've got a very simple example. Let's say that I've got two binary variables, x1 and x2. So the network is essentially showing the computation I would do from the leaves to the root, but it turns out that depending on how I initialize the leaves, I might be able to compute the answer to a probabilistic query. So for instance, if I'd like to know what's the probability that x1 is true and x2 is false, then what I can do is simply set the leaves accordingly. So here with x1 true, I'm going to set x1 to 1 and not x1 to 0. And then with x2 false, I'm going to set not x2 to 1 and x2 to 0. Okay, so I start with this as input. Then I do the propagation going upwards, so I get those numbers for these intermediate nodes. Then I get these numbers after that, and finally at the root, I get a number of 34.8. Okay, so now you might say, well, that's not a probability, so what's going on here? Okay, it turns out that this is the numerator of a probability, so we're going to divide by some normalization constant, and then we're going to get a probability. So this is a first pass. And I'm going to do a second pass through my network to obtain the normalization constant and turn this into a probability. So the normalization constant, intuitively, is going to be the constant that corresponds to summing all the contributions of all the possible worlds. So here I'll want to consider essentially all the joint instantiations of x1 true and false and x2 true and false. So to do this, I'm actually going to set all the leaves to 1. So when I set all the leaves to 1 for binary variables, it does correspond to marginalizing out all of those variables, and then I can obtain my normalization constant. So then I'll do a pass in the same way, and then I get at the root a number, 100, and there we go, that's my normalization constant. Yeah?
Won't you run into a lot of problems if you start using univariate distributions as input?
How are univariate distributions a problem here?
Well, in this case, you can marginalize by setting all of your inputs to 1. But if you were taking a Gaussian variable, then it can take any value on the real line.
Right. Okay. Yeah. So that's a great question. So here, essentially, what I've done is I'm using intuitively Bernoulli variables here. That we can replace these by Gaussian distributions. Now, with Gaussian distributions, what I'd like to do is essentially perhaps set them to some value and then ask what is the probability of that value according to that distribution, and that's going to be a number that's going to be different than 0 or 1. Okay? So this would be the natural way to start with univariate distributions in the bottom. But then when I want to marginalize these univariate distributions, then I would essentially do the same trick. I would set all the leaves to 1, because when I marginalize a distribution, it's like integrating out that variable, and that gives me 1. Yeah. Okay, any other questions? Yeah.
Sorry, I'm just wondering, how can x1 bar and x1 be 1 at the same time if they're binary?
Yeah, okay, so this is because here what I'm effectively doing is computing the probability of x1, x2 both true, plus the probability of x1 true, x2 false, plus x1 false, x2 true, plus x1 false, x2 false. So I'm effectively computing all of those combinations simultaneously, and then, okay, it might not be apparent, but when I do this, setting all the leaves to 1, that's effectively what I'm doing.
But this only works in the binary case?
Yeah, well, okay. This works in a binary case, and then in fact it works for all the cases where the leaves are distributions, because what happens is that effectively I want to marginalize out, or I want to integrate out all of my variables, and when I do that, if the leaf is a univariate distribution, its integral is going to be 1 by default. Yeah. Okay. Good. So now with this example, what should have become clear is that, you see, to answer this query, I did 2 passes through the network. So as a result, to answer the query, I just need linear time with respect to the size of the network. And so it means that the complexity is definitely going to be tractable. So in fact, it's just linear complexity. Okay, so now let's look at the semantics of the network. Okay, so here it turns out that in general, we can interpret every node as computing the probability of some features, a subset of the features that are part of the input, okay, in some context. And this interpretation is going to be valid as long as I satisfy some conditions that are going to be known as decomposability, as well as completeness, or otherwise known as smoothness. Okay, so in general, if you just make up an arbitrary network of sums and products, and then you apply the algorithm that I just showed you before, you can compute something, but the question is, will that be a correct answer in the sense of giving me a probability that is part of a joint distribution, and then will all my answers be always correct? And the answer is, in general, no. So we have to satisfy some conditions, and these are the conditions here. So for those conditions, to define them, I need to define first a notion known as the scope. So here, the scope of a node is going to be the set of variables in the sub-SPN rooted at that node. So for example, so x1, its scope is obviously going to be x1. Now if I look at this sum node, its scope is also x1. If I look at this product node, now it includes x1 as well as x2, and so on. So the scope is essentially the set of variables that are part of the sub-SPN under that node. Okay, now that we understand scope, we'll say that a product node is decomposable as long as its children have different scopes. In fact, disjoint scopes. And then a sum node is going to be complete or smooth as long as its children have identical scopes. Now you might wonder, why on earth do we need to satisfy those conditions? Like, why are they defined in this way? So there's a simple interpretation where if I have a sum node that has the same scope for the children, I can then interpret the sum node as really being a mixture of the children. So here you see, I can interpret this as a univariate distribution in x1. So this one essentially is a degenerate distribution where I'm saying that x1 has to be false. This one would be a degenerate distribution where I'm saying that x1 is true. But overall, these are univariate distributions in x1. And now when I have the sum of 2 times this univariate distributions plus 8 times this univariate distributions, I'm effectively computing a mixture. So here would be a weighted combination of those distributions. But then once they're normalized, right, then this weighted combination is really just a mixture. And I can get this mixture interpretation as long as the children have the same scope. Because if this is a distribution in some variables, let's say x1, and then this would be a distribution in some other variable x2, how can I take a mixture of distributions that have different scopes, right? That would not make sense. But if they have the same scope, then it's all good. So it's a regular mixture, and this works out nicely. Now for the product node, the reason why we would consider this notion of decomposability is that here we interpret the product node as essentially taking the product of two marginal distributions that have different scopes, such that when I multiply them, I obtain a joint distribution that simply happens to be factored, assuming some form of independence. Right? So you see this product node up here has two children. This child has a scope of x1. This child has a scope of x2. So I'm effectively taking the product of two marginal distributions, one in x1, one in x2. And then, as a result, I have a joint distribution, but it just factorizes with respect to x1 and x2. If the children did not have this joint scope, I would be multiplying two distributions that overlap. And now, I mean, there would be ways, in fact, to make a valid distributions out of this, but at least I could not think of this as just the product of two marginals. Okay? So that's the reason why we consider decomposability here. Yeah?
Can you give an example of an invalid scope?
Okay, so invalid scope. So let's say I was just going to change this here. Instead of being not x2, let's say I change it to not x1. Right? Then now I would have a sum of x1 and x2. This would not satisfy the completeness property. And then also when I take the product, so here I would have a product of x1 times a product of something in x1 and x2, and it would not satisfy the properties again. So this would be invalid.
But that's not the property of the scope, right? That's the completer smooth.
Oh, sorry. Right. Okay. Yeah. So these are properties: decomposability and completeness. Now, scope itself is not a property. It's just a definition here that I'm using to define decomposability as well as completeness and smoothness.
Is there a reason that all of your weights and the sum nodes are adding up to the same number? Is that a requirement, or is that just something that makes it nicer? Or?
Yeah, no, that's not a requirement. That was just for the sake of making a simple example. Okay. Yeah, because here I guess it's easy for me to think in terms of 10, 10, and 10.
Sure,
okay,
that's
but
the coincidence.
yeah, it's just yeah, there's no reason. Okay, so in any case, now you see with this, it becomes clear that sum nodes and product nodes are computing probabilities, and then when I normalize based on the normalization constant, right? So you see I wrote here that normally we would compute 8, but then there's a normalization constant when we do the second pass where we would divide by 10, and now this gives me, you see, a probability of 0.8. And then so that's what this node is effectively computing, and as a result, you see we can now understand better what is being computed. In other types of neural networks, I mean, you would compute something, and then what does that number represent? Who knows? It's always difficult, or at least there's no systematic fashion. So sometimes what happens is that you might be able to plot something that would describe how this numerical value relates to the inputs, but there isn't a nice mathematical way of interpreting the numbers. Right? So to interpret the numbers, normally you'd have to have like a scale and some units. In this case, we do have that. Right? So all those numbers are going to be probabilities, and these are probabilities with respect to the scope. So we know what we're computing here. Yeah?
So the notion of decomposability makes sense for either product or sum nodes, right?
Yeah.
Okay, it's just that they're only interesting for product nodes.
So why is it only interesting for product nodes?
Well, because, I mean, then intuitively you're sort of taking apart the product with some sort of independence, right?
Yeah, yeah.
Okay. But for sums, I mean, I can't imagine what decomposability would say.
Oh, yeah, that's right. So here, yeah, decomposability is only for the product node, right? And then for some nodes, instead we want completeness, smoothness, because that allows us to interpret them as mixtures.
Right. But the definition works for either type of node, is what I'm saying.
Oh, yeah, if we wanted to, we could ask, is a sum node decomposable but the answer would always be no, because normally you see, in order to, like the sum node, you want it to have identical scopes. So if it has identical scopes, then it cannot be decomposable, right? So like, I mean, we could apply the definition, but it just wouldn't be interesting. Yeah. Okay. All right, so now that we've defined this, we understand the semantics. The other interesting thing is to compare how we do computation with a regular neural network versus a sum product network. Okay, so in a regular neural network, what happens is that you have some inputs, and then you propagate, you go through the computational graph, and then you produce some outputs. And essentially what the neural network is, it's a function, f, of the inputs that produces the outputs, right? So it's just a function. Okay, and now the issue is that this function is rigid in the sense that you can't quite change it. Like the neural net is typically trained with inputs, outputs, to find out a good function that would approximate whatever is needed normally to go from the inputs to the outputs. So you get f, or at least an approximation of f. But then if you wanted to query your network differently, maybe change what would be the inputs and change what would be the outputs, then you've got a problem, right? It wasn't trained for that purpose, and then it's not flexible. Now, in the case of some product networks, there's actually a lot of flexibility. So here, I can define the inputs and the outputs at the time of the query. It's not at the time of training, right? So I can train my network. We're going to see in a moment how we're going to do this. But once I've got the network, then I can use it to answer arbitrary queries of the type, the probability of some variable given some evidence. And here you see the evidence. You can think of it as inputs. And then the variable that is being queried is essentially the output. Okay? So now, if I want to have x1 as input and x2 as output, what I would do is simply set the values of x1 and x2 in a certain way that would allow me to compute this. So here, when I have a conditional query like this, I can rewrite it as a ratio of a joint query divided by a marginal. And then for the joint query, here I would like x2 false, x1 true. We've already seen how to do this. So you just set those values like this, do a bottom-up pass, and then you obtain a numerator. And now for the denominator, I'm going to do another pass. This time, I'm interested in a marginal of x1 true. So I'm going to start over, where I'm going to set only x1 to true, or x1 to 1, and then not x1 to 0. And then because I want to marginalize out x2, then I will set both x2 and not x2 to 1. Okay, so whenever I want to marginalize out a variable, that's effectively what I do. I set both values to 1. And then I do another bottom-up pass, which is going to give me my denominator. Okay, so you see this is very interesting because here there's no notion of the inputs being at the bottom and the outputs at the top. So in a sum product network, all the variables are always at the bottom. It's just at the time of the query, you decide what is really going to be the input. That's usually your evidence, right? And what is going to be the output, which is your query variable. And then you can answer any query in this fashion. Any questions? All right, good. Okay, so now let me highlight some of the relationships between sum product networks and other probabilistic graphical models. So we've seen earlier that there are Bayesian networks, Markov networks, and it turns out that we can take any sum product network and convert them into a Bayesian network. So here I've got two examples. So I've got here a sum product network of this shape, and then it turns out that this one is equivalent to a naive Bayes model. So a naive Bayes model would have, let's say, a bunch of features, x, y, z, and then a hidden class h, and then it turns out that you see the equivalent sum product networks has this shape. Okay, so the idea is that we can think of the hidden class as really a mixture of the features, and then so here H essentially is replaced by this sum node at the top, and then the features are all at the bottom here. Okay. Now if I want to have a product of naive Bayes models, then it's very simple. I just take this and then duplicate it and then take a product. Okay. And then so the corresponding Bayesian network would be that we have one naive Bayes model, another one here, and then they would be essentially independent naive Bayes models, so that would be the representation. Okay, so in general, I can take any sum product network and then I can convert it into a Bayesian network, otherwise a Markov network, and then in some previous work that we published in 2015, we showed that this conversion can be done without an exponential blow-up. So if anybody, is uncomfortable with some product network and would like to know how does that correspond to other types of probabilistic graphical models, then we've got in that paper a procedure that explains how you can do the conversion. Now you can also go the other way around. When you go the other way around, though, there is a blow-up. And so here, if you start with a Bayesian network and then you convert that to a sum product network, there might be an exponential blow-up. So this is where there's some interesting differences, at least in terms of the representation. And then the conversion to go back is that here you see we represent what are the correlations or probabilistic dependencies, whereas here we represent what we're going to compute. So the conversion to go from a probabilistic graphical model to a sum product network is simple in the sense that if you run any algorithm to do inference, then, and you simply write down the operations you would do in that process, these operations are naturally going to be sums and products, and then if you organize them according to the order in which you would perform them, then you would obtain a sum product network. So that's one simple way of converting any probabilistic graphical model into a sum product network. And then the reason why there might be an explosion is simply because inference in these can be exponential, so as a result, the corresponding sum product network might blow up, it might become exponentially large. Okay, so to summarize, here we can look at sum product networks and other classes like Bayesian networks and Markov networks as follows. So in general, what's interesting is to categorize these representations based on whether they are compact and tractable. So here I'm going to define compact as simply meaning that the space taken by the representation is going to be polynomial with respect to the number of variables in my joint distribution. And then tractable will be that the time to do inference for any query is also going to be polynomial in the number of variables.
By space, do you mean like memory?
Yeah, I mean memory. So if you store the sum product network or the Bayesian network, right, what would be the number of bytes that you would need to represent that? And obviously, I mean, the number of bytes could vary based on the precise representation, but I mean, if we look at the order of complexity, would that be something that grows polynomially or exponentially with respect to the number of variables? Okay, so in general, probabilistic graphical models can represent arbitrary distributions, and then so they all have the same expressivity. Okay, so this outer circle is essentially the space of all joint distributions over some set of variables. Okay, and then they can all represent that. Now the problem is that not all of those models are compact and tractable. So those that are compact are obviously going to be a subset. Okay, so here we've got this space of compact Bayesian networks, so those that you can represent in your computer with an amount of memory that simply grows polynomially with the number of variables. Now the problem is that compact Bayesian networks are not necessarily tractable, so the tractable Bayesian networks are going to be in fact an even smaller subset. Okay, so they're the red circle here. These are the tractable Bayesian networks. So those represent distributions that can be represented efficiently and with which we can answer any query in a tractable fashion. Now if we compare that to sum product networks, it turns out that sum product networks, in their case, compactness and tractability are the same because when we answer a query, we saw that it takes linear time with respect to the size of the network, so it means that as long as it's compactly representable, then you can answer any query as well tractably. So sum product networks that are compact or otherwise tractable are all in here. Yeah.
So obviously from the definition that you've given, since every sum product network is a tractable Bayesian network, that would mean that the set of all tractable sum product networks is a subset of the tractable Bayesian networks. But this seems to imply that it's equal to the set of tractable Bayesian networks. So does that mean every tractable Bayesian network can be represented by a sum product network?
Yes.
Oh, okay.
Yeah, so yeah, every tractable Bayesian network, so if it's tractable, according to the definition, it means I can answer any inference query in polynomial time. Answering an inference queries means I'm going to do some multiplications and additions, and then if I simply cache these operations in the order in which I would perform them and write down the expression that would result, then this would be a sum product network, and then it would take a space that would be the same, or at least the same order as the time it took to do the operations. So that's how any tractable Bayesian network necessarily corresponds to a compact and tractable SPN. Okay? Yeah.
So I just want to confirm, does this mean that if I take a sum product network, convert to a Bayesian network, and then convert back, I'll get the same thing back?
Okay, yeah, that's a good question. So in theory, we should be able to design such a procedure. Okay. Now in practice, that might be a little more complex simply because here you see Bayesian networks, sum product networks are simply representations for a distributions. Now there might be multiple representations for the same distribution. So sometimes what happens is that you start with one representation, let's say a sum product network, then you convert it to a Bayesian network, and now after that you say, all right, let me convert it back to a sum product network, but then it might end up with a new representation that is different, but it encodes the same distribution. Okay, so that's why, like in terms of implementation like this, it might not get back to the same representation, but at least in theory, there exists a procedure that would allow you to do that.
I mean, so ordinarily in logic, what you do is you define a normal form for your class of things, right? So is there a normal form for some product network given the... Right.
Okay. Yeah. That's a very good point. So there is a notion of normal form for some product networks, but unfortunately, it's not sufficient to obtain something unique. So I guess, yeah, here we would need to have like a canonical representation that given a distribution, there is a single representation that goes with it. But the normal form is essentially simply that all the weights are going to be between 0 and 1 and sum up to 1. Okay, so that's what is known normally as a normal sum product network, but that's not sufficient. We need something even stronger for that. Yeah. Okay. All right, so now let's talk about how we can estimate parameters from data to obtain the weights of the sum product network. So graphically, we can think of the problem as follows. So I've got here my data. Okay, so this data perhaps has a set of attributes, and then there's many instances. So here, every column would be essentially a data point, right? And then every row would be a different attribute. Okay, so based on some data, now I'd like to estimate the weights of my sum product networks. So each one of those interrogation mark, right, is simply an unknown weight that I would like to estimate, right? So the parameter estimation problem is precisely how can we get those weights. Now there's lots of algorithms that one can use, and then in general, most of them are going to use the principle of maximum likelihood. So you can use stochastic gradient descent. There's also expectation maximization, signomial programming, and several others. And then you can also use a Bayesian learning technique, like Bayesian moment matching. There's also collapse variational inference and others. So what I'll do now is explain how we can view this as a form of signomial programming, and then after that, I'll explain how we can use also Bayesian learning with Bayesian moment matching. Okay, so all right, so yeah, in fact, okay, before I explain the details for how we're going to do the inference, let me just tell you a bit about language modeling. Well, some of the applications. So over the years, there's been several applications. They include some in computer vision, like image completion. You can also do activity recognition. I'll talk about language modeling. There's also speech modeling, mobile robotics, so there's a wide range. Okay. So for language modeling, in 2014, there was an interesting paper that was published where they proposed the following sum product network to essentially emulate an n-gram model. So an n-gram model in natural language processing is essentially a model where you have, let's say, n words, and then you're trying to predict what the next word is going to be. Okay? So this is a basic task in coming up with a language model. And you'd like this to be as accurate as possible. And then so here, we're not necessarily going to take just the last n words, but in any case, we can take a window of previous words, and then we can feed this through a sum product network, and then compute a distribution over the next word. And then so this particular network was proposed. There's some sums, there are some products. The paper explains what is the intuition in terms of how we designed this structure. I personally was not able to follow the intuitions, but in any case, this is the structure that they came up with. And then they trained it using a form of gradient descent that did discriminative learning. Okay, and they obtained the following results. So we've got the sum product networks down here. You've got some alternative techniques that are either based on neural networks or otherwise even earlier techniques that are simply statistical techniques. Okay. So here, what is being compared is the perplexity. So in this case, a lower number is better. Perplexity is related to the likelihood of a data point, but in this case, what perplexity means is simply that it's a measure of how surprised the model is about seeing a particular data point. So if the model is good and it can explain the data well, then it would not be surprised, and then in general, you see its measure of surprisedness or perplexity should be low. So that's what this shows here. So they explained, well, they obtained very good results, and then they compared, for instance, to latent digital allocation augmented with a recurrent neural network. There's a plain recurrent neural network. There's some more traditional neural networks, and then there's some other techniques from information retrieval and natural language processing. Yeah?
What kind of RNN did they compare against? Like, was it an OSTM, or was it a sequence model, or was it just a...
Okay, great question. I did not do this work. I do not remember the details, but if you go to that paper, they have the citation, and then I guess they explain what that recurrent neural network
But
did.
like, does this in general perform better than cutting-edge neural network techniques at the same task?
So at least at the time, yes. Now, we've got some people in the lab that are actively trying to reproduce those results, and as you can expect from most papers, right now we're not able to reproduce those results, and then so we're not sure what's going on. So we're trying to figure out, I guess, how those results were being obtained. Yes?
I had a more general question about the structure of their SPN that they drew in this paper. Just from earlier, you said that an SPN is in general an alternating sums and products, but they had like 2 layers of sums in a row, so it's not necessarily one sum then one product, is it? It's
Right, so yeah, so here, whenever you've got sums in a row like this, it means that you could collapse this into just one layer of sums. right? Because it just means that you've got some linear combination. So why did they do this? Maybe from a modeling perspective, it was just something easier to comprehend, but from a computational perspective, there's absolutely no reason to do that. Yeah.
When you represent it like this, is it assumed that the transformation to the log space is only happening like before the first layer of sums, then back afterwards? Like you don't take a log again between some layers, do you?
Yeah, that's a good point. So yeah, so here, if we don't have an alternation, then you wouldn't take the log twice, like this. And I don't know in that particular implementation if they were really doing the computation in the log space or not. So in any case, I mean, this is more just to explain the model and then how the computation was done. I mean, there might be all kinds of tricks that are simply not specified. Yeah.
And then, so what does it mean to have some inputs going into the product nodes at the top directly? The Ys.
The Ys. Oh, okay, the Ys up here. Yeah. Okay, so here, okay, so yeah, I can explain this. So the idea is that here we're predicting what the next word is going to be. Then, so every word in the dictionary would have a corresponding Y. Okay, so now the idea is that at the very top we've got a sum, which is essentially a mixture of the probabilities of all those possible words. And then the idea is that the one that produces the highest probability is going to be the correct prediction. Okay, so this is a common trick. If you want to predict a specific variable, then you can simply, like normally all the variables are at the bottom, but I mean you can simply have links from near the top to a bunch of leaves that you just put near the top like this, and these are going to be your variables that you're trying to predict. So here would be the next word. Yeah. Okay. All right, so, okay, so this was an application. Now, yeah, let me go back to the question of how do we do the parameter estimation. So here, if we're going to do maximum likelihood, the objective is essentially to maximize the probability of some query variable, or at least maximize the probability of some input x given some weights. Okay, and then the weights are what we're trying to optimize here. So, yeah, so we're trying to essentially find the weights that would maximize this, and mathematically it would decompose in this fashion. So we have, you see, the first pass that gives us the numerator, and then the second pass that gives us the normalization constant. Now, this optimization problem is not an easy one in general, so we can show that the optimization is non-convex. So this would be a mathematical representation of this. And then in this particular representation, we also assume that we're working with some product networks in a normal form where the weights are going to be, actually no, sorry, no, we don't assume that they're going to be in a normal form. So the weights in general have to be positive. If we have negative weights, then we can't interpret a weighted combination as a mixture. So that is one of the constraints in general, that the weights here have to be positive. Okay, so that's our optimization problem. It might not be apparent, but in any case, you can show that this is non-convex. And this comes from the sum nodes that introduce mixture distributions. And whenever you've got latent variables with mixtures, that usually leads to a non-convex optimization problem. Okay, so how can we tackle this non-convex optimization problem? So last year, with one of my former students, Hans Zhao, so we had a paper where we described various relaxation of this that lead to different algorithms. So for instance, the most popular algorithm, which would be gradient descent, is at the top. So here, we have to modify gradient descent so that the weights are positive. So that's why it's PGD stands for projected gradient descent. But in any case, it's just gradient descent where we project by always just rounding up everything to be positive. And then you can show that here, gradient descent, is really just making a linear approximation on the objective. And then when you do an update based on the gradient, you're doing an additive update. Okay? Now, this is the simplest form of approximation you can do. There's some other approximations. So here we've got the exponential gradient technique. The main difference is that it does a multiplicative update, and then it naturally takes into account the fact that the weights have to be positive, so we don't have to do any projection. There's another one here, sequential monomial approximation. So that comes from the fact that the objective, I mentioned earlier that for a sum product network, we can think of this as a polynomial, but then that polynomial could be approximated to a sequence of monomials, and then it leads to another algorithm. And then finally, we've got another one here where the objective can be seen as a difference of two convex functions. So we can use a convex-concave approximation, where essentially we come up with a concave lower bound. And when we do this, it actually corresponds exactly to the expectation maximization algorithm. Okay, so then we had a paper where we described how all of these algorithms arise. And then in terms of results, this is what we obtain when we compare the algorithms. And as you can expect, gradient descent, is the simplest algorithm, but it doesn't perform so well. So here, all of these plots essentially show how we can minimize the negative log likelihood. So here, lower is better. And we'd like to converge as fast as possible. And then we've got in red projected gradient descent, which does not perform very well. And then at the other extreme, we've got the convex-concave procedure, which corresponds to the EM algorithm, which converge much faster. In fact, in this case, you can show that it has a superlinear convergence rate. Okay, so this shows that you see we can obtain different types of algorithms. We don't have to stick with gradient descent, and then we can obtain much faster convergence rates depending on what we use. Yeah.
When doing your parameter estimation, so if you view the lower sum nodes in the network as sort of encoding their own more compact distribution among just part of the total number of variables, can you do your parameter estimation on those individually first and then move up the tree, since their output shouldn't really be impacted by what's higher up the tree?
Yeah, that's a good question. Yeah, can we do the parameter estimation just on those at the bottom first? So I'm sure we could do something local in this fashion. Most of the algorithms, like including gradient descent, they have to do like a complete pass-through, and then information is being propagated from the root down and then back up again. So it's actually, you could do something that's local, but at least all of those techniques tend to be global in the sense of using information throughout the network. Yeah. Okay. Okay, now let me move on and talk about what if we have streaming data. So you can use a sum product network, or you can use neural networks to estimate a model from data. But now if you've got streaming data, what it means is that you would like to be able to update your model after you receive each data vector. So if you want to do some traffic classification, for instance, there might be flows of data packets between different computers. You might want to do some predictions based on that. And traffic is happening continuously, so you can get data continuously. If you're doing app recommendation, so each time a user is presented with a recommendation and either accepts it or not, that's a new data point that can be used to update your model. And you'd like to be able to simply update as opposed to recompute from scratch. Okay, so then the challenge is, how can we update a model if we receive data one data point at a time? And this is interesting because with large models, again, you don't want to recompute everything from scratch. You just want to be able to update on the fly. Okay, so here I'll describe an online technique for some product networks that allows us to update the model, or at least update the weights on the fly as we receive the data. Okay, so now being able to do things in an online fashion like this is interesting because not only is it useful for sequential data, but also in terms of making things scalable, it means that you can just stream the data. You don't have to load everything at once, and then you might be able as well to distribute some of the data. Okay, so in classic neural networks, you can use stochastic gradient descent, and then this algorithm will allow you to update after you process every data point, and there's no issue with this, except for the fact that gradient descent is not a very good algorithm. Okay. Now, in the algorithms that I mentioned earlier, so there was also the exponential gradient algorithm. There's also the EM algorithm that we just discussed. All of those can be turned into online algorithms, but it turns out that all of those algorithms, they suffer from the fact that they lose information from when they process data in mini batches. So normally all of those algorithms, they have some data, then they do some updates based on each data point, but then they would do multiple passes through the data. And then you can turn these algorithms into online algorithms simply by splitting your data into mini batches and then feeding one mini batch at a time, doing some updates, moving on to the next mini batch and so on. But when you move on to the next mini batch, you forget about the previous data. And that means there's information loss. So an interesting question is, can we do better? So here, we're going to get some help. And does anybody recognize who this is?
It's claimed to be a portrait of Thomas Bayes, but no one actually knows who this is.
Okay, very good. Okay, yeah, so this is a portrait of Thomas Bayes. Okay, perhaps we don't know if it is indeed the correct portrait, but I mean, it's all over the web, and whenever people talk about him, that's the picture they show. Okay, so we've got Thomas Bayes. Now, what is he famous for?
Bayes theorem.
Bayes theorem. Okay, so here, you might ask, like, why do we care about Bayes theorem at this stage? I mean, Thomas Bayes essentially proposed Bayes theorem back in 1764, and now we're in 2017, and how can something so old be still relevant today? I mean, okay, maybe it's foundational, so that's why it's relevant, but still, is there something about Bayes theorem that, you know, has become, in fact, quite interesting and gave us an advantage just recently? So the answer is that we can, in fact, use Bayes theorem to do parameter estimation in an online fashion with streaming data without any approximation. Okay, so this is pretty neat. And it turns out we can also do distributed computation very naturally based on Bayes theorem. So there's lots of algorithms that are based on mini batches, but then whenever they use mini batches, there's information loss. I'm going to show you now how you can do online learning and distributed computation without information loss. Yes?
Is this just for SPNs or in general?
This is in general. Yeah. So in fact, people are now starting to appreciate this. Like there was a paper in 2013 by Broderick that essentially highlighted this. In the community, most people are still not very, they don't realize that this is such an important result, but it's starting to become more and more understood. Okay, now let me show you mathematically what I mean here. So for online learning, based on streaming data, if we're doing Bayesian learning, what it means is that we would start with normally a prior, right? And then update that prior to obtain a posterior based on the likelihood of the data, right? So here, this is Bayes' theorem that allows us to go from a prior to the posterior using the likelihood. Now, if I want to do this computation with streaming data, it means I'm going to get one data point at a time. So I can start with my prior, and then when I get my first data point, then I can update my posterior based on the likelihood of that first data point. Okay? So I can just do an update with that data point. Then when I get my second data point, I can revise again. I can just multiply my previous posterior by that likelihood, get a new posterior, and that's my new update. And then I can keep on going like this. So because Bayes' theorem naturally factorizes, or at least the likelihood of the data naturally factorizes whenever you make the assumption that the data is IID, then it means that you can do online learning naturally using Bayes' theorem. So this is beautiful. Yeah?
Is this essentially updating the prior every single time we get the data point?
Yes. Yes.
Is the IID assumption reasonable in, say, like the traffic case where it's sequential observations are likely to be highly correlated?
Okay, so I guess, yeah, here when I said IID, what I really mean is that it should be independent, conditioned on your model. Okay, so if the data is indeed independent given your model, then we're fine. And most models, in fact, do make that assumption. Now, you're right that if we have a sequential process, it might happen so that one data point really is correlated with a previous one and so on. And this is, regardless of what model we use because it's sequential data. So here, yeah, we have to, yeah, so we might have to do some further assumptions to break that. Yeah. Yes?
What about normalization factor here?
Oh, okay, yeah, so here I did not include the normalization factor. But I mean, it's something that can always be computed on the fly. And so here, yeah, I mean, it does not really impact the result.
How come it can be computed on the fly? Because we have to compute the marginal after basically receiving every single new point, right?
Well, okay, so it depends what the goal is. So let's say your goal is to do classification, so you're trying to make a prediction. Then in fact, you don't even need a normalization constant because you just want to know, like, what's the magnitude of every possible class, and you can just go with that. Now, if you do need to have the marginalization, the normalization constant at every step, in the context of a sum product network, then, I mean, it would correspond to one pass, so you could do an extra computation to get that. But then that extra computation would not depend on how much data you've seen before. It would just depend on what is the size of your model.
Yeah, but if it's not some product network in general, I'm not sure how easy it is computing this normalization factor after it's
Okay, yeah, that's a fair point. So yeah, depending on what the model is, let's say we want to do this in a context of Bayesian networks or Markov networks where the normalization constant is not easy to obtain, then yes, there would be some issues. Yeah. Okay. Now, if we do distributed computation, there's something similar that happens where what I can do is take again my equation, or at least the computation I would do for the posterior, and then I can simply partition my data where perhaps I can take the first core to do this computation, the second core to do this computation, the third core to do this computation, and then after that I just multiply everything together. Okay? So here you'll notice that, okay, the first core gets to have the prior, and the other cores don't have the prior, but having no prior is essentially the same as saying that I start with a uniform prior. Okay, so if you wanted to, I guess, make sure there's a prior everywhere, you could have your true prior here, right? And then the others could just have a uniform prior, something constant, so that then you're effectively still just doing Bayesian learning. And then after that, you can multiply everything together, and there's no problem. Okay, so this is beautiful in theory, in the sense that, unfortunately, Bayesian learning will be intractable. Okay, so we're going to have to do some approximations, but at least in theory, there's no issue. So all the questions of how can we handle streaming data, do distributed computation, are already answered. But now we're going to have to do some approximation, and then the question will be, can we preserve some of those as well as possible? Okay, so yeah, when we do exact Bayesian learning, what happens is that we have normally a prior, and then we multiply by the likelihood. That gives us a posterior, and then depending on what is the underlying model, for instance, in the case of some product networks that have binary variables, we could use the family of Dirichlet's, and then we would get in the posterior an exponentially large mixture of Dirichlet's. Okay, so that becomes problematic because the mixture would grow. It would grow by a factor that would depend on how much data I have. In fact, it would be exponential with respect to the amount of data. Okay, so that's not going to scale. Okay, so for this, we're going to need some help. And who recognizes this other famous statistician? No. So yeah, I guess his picture is not as widely used as maybe Thomas Bayes. No, it's not Thomas Box. Sorry, it's not Box, but sorry, say that again.
Start with P.
Yeah, so his last name starts with P.
Pearson?
Pearson. Yes. Okay, so what is he famous for?
T-test.
Right, so okay, I guess there's a correlation test, and then there are the p-values and so on. But it turns out that Carl Pearson also has some very important contributions with respect to parameter estimation. And when it comes to estimating parameters from data, if you take any book of statistics, one of the first techniques that is described is the method of moments. Okay? So the method of moments, for instance, let's say that you've got some data and you'd like to estimate a Gaussian from data. What you would do is simply compute the empirical mean of your data, the empirical variance of your data, and then simply just declare that the mean and the variance of my Gaussian correspond to that empirical mean and empirical variance. Okay, so this is known as the method of moments because many distributions can be described by a set of moments, and then so estimating them really corresponds to simply estimating from data the moments, estimating some moments from your data and then setting the moments of your model in this fashion. Okay, so yeah, that might not sound too exciting, but very recently there were some major breakthroughs where when it comes to estimating parameters or estimating parameters of some mixture models from data, we had the first provably consistent techniques based on the method of moments in the context of hidden Markov models, mixtures of Gaussians, as well as latent Dirichlet allocations. Okay, so these are all classic models that have been around for a long time, and traditionally you would estimate them, let's say, using maximum likelihood or some other technique that would do some optimization, but then the optimization would be non-convex, might get stuck into a local optimum, and then it would not necessarily recover the true underlying parameters because that would require conversions to the global optimum. Okay, so now using the method of moments, we can formulate things differently, and then we have been able to show that with enough data, in fact, in the limit, an infinite amount of data, we can recover the true underlying parameters. Okay, so this is something quite powerful and quite important both from a theoretical and a practical perspective. Okay, so in this work, what we did is we decided to combine together Bayesian learning with the method of moments. Okay, now that might not sound like a good recipe because we're essentially taking a frequentist with a Bayesian together and asking them to work, but in any case, as practitioners here, we're not going to worry too much about this, and it turns out that this is an interesting approach that can yield some good results. Okay, so by combining these two techniques together, we'll see that we'll obtain an algorithm that is online and distributed based on what we've seen for Bayesian learning, and then it's going to be tractable as well, and then so this will come from the fact that now we're going to approximate our intractable posterior by matching some moments and obtaining a projection onto a tractable family of distributions. Okay, so tractability will come from the method of moments. Okay, so the general approach is that in general, here we would obtain a mixture of products of Dirichlet that can be exponentially large, and I'm going to project that at every step to obtain a single product of Dirichlet by matching some moments and then obtaining something that is tractable. And the moments I'm going to match are just the first and second order moments. Okay, so graphically, the algorithm would work as follows. So I start with a prior, let's say that is a product of Dirichlet. Then I do my Bayesian update, so I do exact Bayesian learning, and I would obtain a mixture of products of Dirichlet. That mixture, now I'm not going to let it grow too big. At every step, I'm going to project it down immediately to a single product of Dirichlet. So this is where I'm going to do an approximation, but that approximation, I'm going to make it in a way where I'm going to match the first and second order moments of my distributions so that at least I retain, some good statistics. And so this will work well. This will ensure that I don't have any intractability. And I'll show you in a moment some empirical results that shows that this works well.
So what's that upper?
Oh, the Bayes update. This is just applying Bayes' theorem where we go from a prior to a posterior. So we've got a prior, we have a data point, we compute a posterior, and that's just based on Bayes' theorem.
So the prior is Dirichlet now.
Yeah.
And then you have one new data point.
Mm-hmm.
So the posterior, where the posterior is going to be mixture.
Okay, so yeah, I went quickly over this. Let me go back. Okay, so it's based on this equation here. So the posterior is going to be the product of the prior. So the prior here is just this product of Dirichlet times the likelihood, where the likelihood in a sum product networks is essentially going to be a large sum of products of the weights. Okay, and as soon as you've got some nodes in your sum product network, you're going to have a sum here. And then when I multiply these, so multiply this by this, I can essentially collapse together the products, but then the sums are going to come up front here. And this will induce a mixture of Dirichlet. And that mixture is just going to keep on increasing and increasing. So that's at a high level.
Is there a systematic way to do that projection? Or do that projection?
Yes. Well, so the way we're doing it is simply by matching the first and second order moments. So I'm not showing you the math for doing this, but I mean, there's some details here, but it can be done simply by solving a system of linear equations. Yeah. Okay. Let me show you the results, and then we're going to conclude because I think we're out of time. Okay, so the results are here. So this was some work we did in last year. We've got our approach in the middle here. What those numbers correspond is the likelihood of the data. And then so here, higher is better. And then we've got some alternative techniques. So there's here stochastic gradient descent, online EM, online exponential gradient. And then all of those arrows indicate that when there's an arrow down, it means that this result is worse than what was obtained by Bayesian moment matching, and then it's worse in a statistically significant way based on the Wilcoxon signed rank test. Okay. We also compare to Learn SPN, which is an approach that is not online. So as a result, it can go over the data multiple times, and it is possible to obtain better results. In general, it does. But this just shows you essentially what's the gap between an online and an offline technique. Okay, and then these are all data sets that you can download from the web and use for testing. Okay, so, all right, and then we did this as well in larger data sets. So, for instance, you see we've got data sets with hundreds of thousands of variables, and then we were able to apply the online technique, online Bayesian moment matching. And then this column here is the distributed version, where what we did is we took the same algorithm, but we just partitioned the data into 10 different computers, and then got them all to compute a posterior, multiplied that together, and then we obtained the following results. So that's the distributed version. And the results are slightly worse simply because in theory it should be identical if there's no approximation, but the computation is not exact, it's approximate, and then that approximation will be amplified once we distribute the computation. Okay? And then you've got the running times as well here that shows how this scales. Okay, so, all right, I had another section on structure estimation, but we don't have time, so I'm just going to quickly go over this, and we're going to conclude. Oops. Okay, here we go. So today we talked about sum product networks. So it is a special type of neural network, and hopefully I've convinced you that this special type has some clear semantics, but it's also a type of probabilistic graphical model that has some interesting properties. And then so there's some other work, for instance, that other researchers here in my group have done in terms of extending some product networks for decision making, but also in terms of making them recurrent, similar to recurrent neural networks. And what we're currently working on is a PyTorch library for some product networks. And also, we'd like to apply some product networks in the context of conversational agents. Okay, so I'll stop here, and perhaps I can take maybe one question or two, and then I think we have to vacate the room after that. Okay, any questions? Okay, well, thank you very much.